Okay, how about if we get started today by doing one more of those blasts from the past? Those are always fun. And remember, the purpose is to prepare you for your exam, because these are problems coming from old exams. I assume you've noticed that all the old exams are on Blackboard, right? Okay, but these are just selected problems from the old exams. This is one from just last year, okay? Let's read it off. A voltage source is applied to the left end of a transmission line as shown below. A plot of the generator voltage is shown here. The width of the pulse, so it's a rectangular pulse, the width is 6 nanoseconds, and the pulse voltage, V0, is 5 volts. Okay? So first it says construct a bounce diagram and make it go out to 16 nanoseconds. Okay? Make it on the next page. So in this exam, there was like a graph given where you're supposed to, make the bounce diagram, whatever. But anyway, make an accurate snapshot plot of the voltage on the line. So snapshot means voltage versus distance at a fixed time of 7 nanoseconds. Again, a graph was given in the exam. So, make your plot on that graph and label all voltage values, all right? Okay, now it's a rectangular pulse. So you may remember the method of dealing with a rectangular pulse. The normal bounce diagram is for a step function, just a function that looks like this. Comes up here, and it comes up to V0 and stays V0, right? So to get the rectangular pulse, remember the trick? We make 2 bounce diagrams and we subtract. Okay? Well, if you're making an oscilloscope trace, you don't really need to make 2 bounce diagrams. Just 1 bounce diagram is enough. You make the plot of voltage versus time for the step function, and then you just shift it yourself, right? Subtract. That's the easiest thing to do. When you're making a snapshot, it's best to actually make 2 new bounce diagrams. 2 bounce diagrams, the original one and a shifted one. I think that's the easiest way to avoid confusion, okay? All right, so we'll do that. So here is the bounce diagram and the shifted one. Okay, now let's see. Length was not given in meters, but the time, the transit time was given as 4 nanoseconds, and that's all we really care about. Okay, so notice in the bounce diagram, the first wave takes 4 nanoseconds to reach the end. Then when it bounces back, it'll reach the generator at 8 nanoseconds, and then another 4 seconds, it's back at the load, then another 4 back at the generator, etc. Right? Okay. Now it's good to immediately label the reflection coefficient. So at the load end, it would be 300 minus 75 over 300 plus 75. Which, because of these nice numbers, comes out to be a nice 3/5 or 0.6. At the generator end, because of this impedance right here, the reflection coefficient is 50 minus 75 over 50 plus 75, and that comes out to be a negative number because this value is smaller than this one, and a nice value of minus 1/5. Okay. All right, so first let's make the usual bounce diagram. And so again, we have the times labeled, right, as shown here. Now the incident wave comes from the voltage divider. Now remember the generator was putting out, remember, for the step function, pretend we're doing a step function right now, that's the original bounce diagram, V0, which is 5 volts. But then voltage divider cuts down that 5 volts. What's that, A term going to be, as we call it in the notes? Voltage divider, 75 over 75 plus 50. Okay? So that'll come out to be exactly, if you calculate it, the number 3/5. Okay, which gets multiplied by 5 to give a nice even 3. So 3 volts right here, this number here, this 3 volts is the label for this wave coming out here. That's the incident step function wave coming out from the generator if we're doing a step function problem. So 3 volts comes down, hits the load, reflection coefficient is 3/5. So notice I'm labeling all these waves first. So 3 volts times 3/5 is 1.8. 1.8 comes down, hits the generator, reflection coefficient is minus 1/5. So minus 1/5 times 1.8 is minus 0.36. When that wave hits the load again, it's going to be minus 0.36 times 3/5, which is minus 0.216. So we've got all those black lines labeled. That's all the wave amplitudes of the step function bouncing back and forth. And then the running tally, remember, are these purple numbers. So we start off with 0. This is of course the region that means physically before the first wave has even crossed you. So you don't say anything yet, 0. Then when it crosses you, 0 plus 3 is 3. So this 3 label here is in this triangular region. So 3 volts is going to be the solution until the next one crosses. In other words, you go into this region, and then it'll be 3 plus 1.8, which is 4.8. So 4.8 is in this region. And then when you cross this one here, it's 4.8 minus 0.36, which is 4.44. That's this region. And then finally in this region, 4.44 minus 0.216, which is 4.22. Okay, so that's the original bounce diagram. And that's all we would need if we're just dealing with a step function. We have a pulse, but if it was a step function, that's all we would need, right? Okay, and any questions, first of all, on just that original bounce diagram? Yeah, please. Either way is possible. Either way is possible. If it's making a graph of the voltage, I'm probably more likely to give you some kind of a template. For the bounce diagram itself, I'm not so sure, because probably you can do that yourself without a template. Yeah, probably. But let me say it could be advantageous on the exam to bring a ruler. Could be advantageous. Yeah. So you won't need a compass because we won't have Smith charts on exam 1, right? But I'd recommend a ruler. Okay. So anyway, so is that okay, the original bounce diagram? Now, so we're doing a snapshot. So remember, the pulse is like one step function minus the second step function that starts right here at W, which is 6 nanoseconds. So notice I'm shifting everything down by 6 nanoseconds. Look at the scale here. Here's 4. Here's 8. 6 is halfway in between. That's why I put this dashed blue line at 6 nanoseconds. Okay, so the shifted bounce diagram is starting there. Okay. All right. Now, let's see. Well, okay. So I can see, I cut and pasted this from the solution. I can see there's one mistake on it. I forgot to relabel these times here, right? So the blue line here is 6 nanoseconds, right? So this one should not be 4 nanoseconds, right? Right. I forgot. Maybe I'll correct that on the exams, but anyway. Oh, sorry about that. Okay, but anyway, shouldn't affect the solution though. Okay, so but it said make a snapshot at 7 nanoseconds. That's what the exam is asking us. So we go to 7 nanoseconds. Okay, remember the blue line is 6 nanoseconds. Here's 8 nanoseconds, so halfway between here and here. So there it's supposed to be the dashed red line at 7 nanoseconds. Okay. All right. So now remember, it's this thing, whatever we get from this one, minus whatever we get from this one, right? That's how you do the rectangular pulse. Now, so just take this one. So remember, this is the 3 volt region here, and this is the 4.8 volt region. So it looks like the red line here looks like it's going from the 3 volt region here to the 4.8 volt region here. So 3 to 4.8, and it's crossing right here, which is looks like, so it looks like it's going to be 1/4 of the way down the line. So no, the blue line would be halfway down the line, right? So it looks like the red line is the red one is going to be halfway. I mean 1/4 of the way from the generator. Okay, so here's the generator end. Here's the load end. Here's halfway, of course. So this point right here, this distance right here should be 1/4 of the way down. Here's halfway down. Here's 1/4 of the way down. So 1/4 of the way down the line from the generator, it's jumping from 3 to 4.8. Now that, if you look at, it's kind of hard to see, but if you look carefully, that's supposed to be the solid black line. Okay, this is distance. There's 1/4 of the way down the line from the generator. That's where the solid black line jumps from 3 to 4.8. Okay, see that? Now, I got to subtract from that what I get from the second one. Okay, now the second one, as you can see, is changing from 3 in this region here to 0 in this region here. And it turns out that it's also a quarter wave down. Okay, 7 nanoseconds. It was 1 nanosecond. This is 1 nanosecond here, right? And this is 4 nanoseconds. So 1/4 of the way down, right? This is 1/4 of the way down. It's going to go from 3 to 0. Now that's the black dashed line. Quarter wave down, it goes from 3 to 0. Okay, does everybody agree so far? All right, now then the final thing we do, the final solution shown in red is of course just the black solid line minus the dashed line, right? So notice in this region here, from the generator down to the quarter wave point, you're really taking 3 minus 3, so you're going to get 0, right? And then after the quarter wave point, you're going to be taking 4.8 minus 0, so it's 4.8. So it's going to go from 0 to 4.8. And there you go, that's the final answer. So at 7 nanoseconds, that's what the voltage waveform would look like on the transmission line. Okay. Any questions? Okay. What do you mean?
Just right of the.
Oh, okay. The wavefront. Okay, now this is okay. That's a good question. This is actually kind of an unusual and kind of tricky problem. Let me make a couple comments about it. So, see, the transit time on the okay. Let me back up a second. When you send like a rectangular pulse, down the line, what you normally expect to see in a snapshot is the rectangular pulse will be observed at some point on the line, going to the right or going to the left, right? That's what we kind of expect to see, right? Now, this is kind of an unusual problem because the transit time is 4 nanoseconds, and yet the pulse width is larger than that. It's 6 nanoseconds, right? So it's kind of a weird. That's why the final answer doesn't appear to be a rectangular pulse, right? That's the first comment I could make here. So if I give you a nearer pulse, you would actually see a pulse, and it would make sense to say it's going to the left or going to the right. Now, another interesting thing about this, by coincidence, so this guy here is jumping a quarter wave down, right? And this guy here is jumping a quarter wave down. You see that? But this guy here, the wavefront is going to the left, and this guy here, the wavefront is going to the right, right? So if I let time progress, I'm not going to see this red line moving either to the left or the right. Something really interesting is going to happen. That edge right there is going to split, and we'll see a waveform going this way and a wavefront going this way. It'll be a splitting effect, actually. So it's kind of complicated. Yeah. Not just a coincidence in this particular problem. Okay. Kind of a weird problem. Yeah. If I had to do it over again, maybe I would have picked a narrower pulse. But oh well. Okay, yeah. Well, like I was just answering him, right here, you could not put an arrow here. Because in this weird problem here, you can't say that this wavefront, this jump right here is going either to the left or the right. It's coming from a superposition, remember, of what's going on here and what's going on here. See, just imagine I had given some time other than 7 nanoseconds, then this crossing and this crossing would be at different points on the line. Okay, then you would actually see 2 different jumps, and one is going to the left and one is going to the right. Okay, but this weird problem, you got 2 wavefronts, one going to the left, one going to the right, and at 7 nanoseconds, they're on top of each other. So it makes it kind of a weird problem, right? So this is a weird problem where I can't just put an arrow here and say there's one jump going left or right. No, it's more complicated than that. But that's that's kind of a weird problem. Okay. All right. Anything else? Okay. Very good. All righty. Yeah, I'll try to remember to correct that on the old exam solution if I remember. All righty, but didn't affect the solution. Thank you. All right, so the plan for today is we're almost done with notes 13, but a few slides left, which is kind of interesting. So we'll finish that. We'll go to notes 14, which is a very short set of notes. Shouldn't take too long. And then notes 15 is probably going to be the main topic. We probably won't finish it today, but that'll be the main topic for today, okay? Plane waves. All right, so let's go back and finish off notes 13 first of all. Okay. Now remember that the subject of notes 13 is impedance matching. We saw the different methods, and this is the final thing we did. Excuse me. A single stub matching system. Excuse me, something in my mouth there. Okay. Okay, so this is the final design. We're done with it, unless there's any questions. But now we do one more thing as a follow-up to the example. We're going to make a plot of the standing wave pattern, a plot of the normalized voltage on the line to see what it looks like in this practical, match system. Okay. All right. So here's the answer. Let's see if we can justify how this came about here. Now, first of all, let's recall that when we say normalized voltage, like on the homework, I think I'll be doing this like a homework 6. When it says make a plot of the normalized voltage, this is what it means. Magnitude of the voltage over magnitude of the incident wave, forward going wave, and that always comes out to be magnitude of 1 plus gamma z. So to plot a normalized voltage pattern on the transmission line, this is what you're always plotting, the magnitude of 1 plus gamma z. Okay. Now, the crank diagram is a nice way of doing that. Of course, you could just do mathematically, of course, but the crank diagram is a nice way to do it. So this problem is suggesting we do it with a crank diagram. And, as the notes explain, you can use a Smith chart as a crank diagram. Now, if you want to use a Smith chart as a crank diagram, let me kind of review how you do that. Okay. Now, first of all, there'll be the normalized load. Here it is in this problem again. Okay, we already solved for that previously. You have to go back to find it, but there it is, 2 plus J2. Anyway, that's the normalized load. Now, the red dashed circle is what we call the SWR circle, circle of constant radius. And of course, as you go from the load down the line, remember, you're just going clockwise on the Smith chart, right? Or on that SWR circle. Okay. Now, let's first, don't worry about this stub. This is what we have in the practical match system. But first, let me show you what the standing wave plot would be if we just ignore the stub and just pretend we just had only this line meeting the load. Let's do that first. Okay, that's what this red curve is. Now, so when we do the Smith chart as a crank diagram, then here's how it works. What you're trying to plot here, the magnitude of 1 plus gamma z, that's what this voltage plot is simply the distance from the leftmost point of the Smith chart to where you are on the SWR circle. If you happen to be at the load, we want to be here. But just visualize you're moving from the load back on the line. So visualize that blue dot moving clockwise, and you're always tracking that distance from the left edge of the Smith chart to where you are. That length is the normalized voltage that you want to plot. Okay. Now, as a quick review of why that works. Okay, first of all, I'm using the Smith chart now in the quote usual way as the impedance calculator, not the admittance calculator. So this is what we call the gamma plane, right? This is the real gamma axis, imaginary gamma axis. It's a complex plane, gamma z. Now, think of how you add two complex numbers, 1 plus gamma z. Remember that complex numbers kind of work like two-dimensional vectors. And if I add two-dimensional vectors together, remember that tip-to-tail rule for adding vectors? So same kind of rule for adding complex numbers. So let's just pretend I'm at the load to keep it simple. I could be anywhere in the circle. Let's just say I'm at the load to keep it simple. So imagine a two-dimensional vector going from the center of the Smith chart to where I am on the circle. I didn't label an arrowhead, but you can visualize that as a two-dimensional vector. That represents the complex number gamma z. Okay? Now, going from the left edge of the Smith chart to the center represents the complex number 1, because remember, the radius of the Smith chart is 1. So the tip-to-tail rule for adding two vectors, or really two complex numbers, 1 plus gamma z, the composite vector is this guy right here, right? If you put an arrow here, then that's going to have a magnitude and an angle that corresponds to the complex number 1 plus gamma z. All we care about is the magnitude, so that's this length. So to summarize one more time, wherever you are in the SWR circle, draw a line from the left edge of the Smith chart to where you are, measure that length. That's the same thing as magnitude of 1 plus gamma z, which is the normalized voltage you want to plot. That make sense? Okay. Now, when I say measure this length, be careful. Remember, our agreement is the outer radius is 1, right? So if you're measuring in something like inches or centimeters, what it really means is measure this length in centimeters and divide by the radius of the Smith chart in centimeters, right? Okay, don't forget that. Okay, but anyway, so if you do that, and you really, if this was a real problem, you got your rule and you measured, supposedly this length here comes out to be 1.55. So that's what's labeled here. Right at the low, the normalized voltage is 1.55. Now, a little bit later here, I'll cross the positive real axis, which is always where the voltage is maximum. If you measure that length, what I'm highlighting right here with the pointer, that blue line, that length is 1.62. And that's why the voltage maximum has been labeled at 1.62, right? And that's as big as it ever gets, which corresponds to also saying, you know, perfect constructive interference between this guy and this guy, which is now flat. So it's really just saying 1 plus this distance here, which is the magnitude of gamma L. So that's another way of saying it. The voltage maximum is 1 plus the magnitude of gamma L, but it's the distance from here to here, where the voltage maximum is. And where does the voltage maximum occur? Well, if you read this outer scale, what's labeled as purple here on the Smith chart, remember that's distance going toward the generator, away from the load toward the generator. The load happened to be at 0.178, and the voltage maximum, of course, is 0.250 on a Smith chart. So the difference is 0.042. So that's this distance right here, 0.042 lambda. Now remember, Z is negative, right, on the line. So Z equals negative 0.042 lambda is where the maximum is, right? Okay. Where would the minimum be? Well, quarter wave from the maximum, always. Now, maximum here on the Smith chart, voltage and minimum always opposite on the negative real axis, right? Now, so you read off this distance with your ruler, this distance right here, it's 0.38. And that should correspond to perfect destructive interference between 1 and magnitude of gamma L. So 1 minus magnitude of gamma L, which is 0.38. Okay, and then et cetera, et cetera. Okay. Another quarter wavelength away, another maximum, et cetera, et cetera, et cetera. By the way, this for reference, this is the 1 line. So everything oscillates about the 1 line, right? Maximum 1 plus this, minimum 1 minus this. So the standing wave pattern goes up, goes down, it oscillates about the 1 line, right? In other words, the total voltage is oscillating about the incident wave, if you want to look at it that way. Okay? All right. Now, the red curve would be what we have if we just had this line going on forever. And of course, obviously, it's not a matched system, of course, right? But remember, we designed this system by putting the stub here. We know the distance, we know the length of it, and we expect to see a perfect match looking in from the main feed line. Okay, so the line doesn't go, the main line doesn't go on forever. It goes to distance D, which is 0.219 lambda, and that's when things change because now the stub is there, right? Okay, so here's 0.219 lambda from the load. Z equals minus 0.219 lambda. Okay, and so notice I went 0.219 lambda from where the load is, and that puts me at 0.397 lambda here on this outer chart. Okay, and so that's where this white dot is. And so it's interesting to calculate what is the voltage at this point right here where I'm putting the stub. So in other words, I'm coming back here, I'm looking at the standing wave voltage plot. What is it right when I get to where the stub is? So that's what this white dot is, right? 0.219 lambda away from the load, because that's what we calculated, right? Where to put the stub. So that's this white dot right here. You get out your ruler, you measure it, and it comes out to be 0.78. So right here is where we're going to put the stub. So this red plot doesn't keep going, right? Because that's if you didn't have the stub. We're really going to put the stub right there, right? But the stub is not changing anything in this region right here, right? So the red plot here is good down to this point right here. And then all this has to change, right? Because now you're on the system that actually has the stub, right? Okay. And of course, what happens to the left of the stub? Well, it should be a perfect match if we did the design correct, right? So the voltage should be a perfect, flat, straight line, right? Now, of course, the stub is not going to change the voltage. The stub is a parallel element. So the voltage, KVL law, right? Voltage just to the right, just to the left is going to be the same, right? Okay. And that's this number 0.78. Okay, so here's what you get with the stub. So this part hasn't changed, right? But now here's the stub. Shown here is just a circuit element, but it's really the stub. And then the voltage all the way to the left, going all the way back to the generator, is perfectly flat at a level of 0.78 on this normalized voltage scale. But no ups and downs, perfect flat line. In other words, SWR is 1, exactly what we want. In other words, a perfect match system, right? So the generator thinks it sees a perfect match on this part of the line, perfectly flat voltage, okay? But we know that really between the stub and the load, yeah, it's going to look like this. We don't really care about that, but that's what it looks like. Okay, any questions? Okay. So do you feel comfortable using the Smith chart as a crank diagram now? Okay. Okay, it's not that bad. All right, well, that's it for this set of notes. I'm not going to read this off to you, but oftentimes I like to put helpful appendices, which give a summary of the most important results. I encourage you to read through it carefully, make sure you understand everything in the appendix, because it's a good summary of all the different methods, okay, for doing matching. All right. All right, so if there's no questions, I'm going to close this down and go to notes 14. Now, this is a short set of notes, won't take very long. It's called discontinuity effects. And some of it we've really already talked about in the past. Okay, but it's kind of nice to have one set of notes that kind of summarizes this conversation. Discontinuity effects is another way of saying, when does transmission line theory become approximate? It's not exact anymore. That's another way of saying it, right? And here's that good old Cat5 cable we talked about before, if you remember that. Okay. Okay, so here's the two main effects that transmission line theory does not predict: reflections from discontinuities, and depending on the type of transmission line, radiation from discontinuities. Now, what is a discontinuity? Any deviation from a perfect, straight, ideal transmission line. Okay? That could be a bend. It could be something you put on the line. It could be even the load or the generator. Anything that deviates from a 100% pure straight line. A 100% pure straight line doesn't have any reflections, doesn't have any radiation. You know, the telegrapher's equations predict just a pure wave traveling down the line, right? Okay, until it hits something and bounces back. But discontinuities will cause reflections in general and possibly radiation, possibly. So let's explore this by the two most common examples of real life transmission lines, the coaxial cable and the twin lead. Okay. The coaxial cable is a good example of one that's called shielded or closed because it's got this shield, this braided aluminum shield. No radiation can escape. Well, assuming the thickness of the shield is at least 3 or 4 skin depths, okay, which we'll talk about later. Twin lead, though, is something where possibly radiation can occur at a discontinuity because it's just these two wires running side by side in air, right? Okay, you got a plastic strip supporting them, but basically it's in air. Now for coax, like I said, no radiation can escape because of this shield. Okay. All the energy, in other words, the Poynting vector is totally confined to this insulating Teflon or polyethylene layer, whatever it is. It can't penetrate out, so no radiation escapes. Okay, which is good. Now that's good from an interference point of view. So, you know, the coax will never radiate and interfere with another device or component, nor will it pick up any interference. That shield will prevent it, you know, as long as the thickness is, you know, more than a few microns, right? Thick compared to a skin depth. That's why I said before, coax is kind of the gold standard if you really don't want to have any EMI, any electromagnetic interference. Okay. Now, even though it doesn't radiate, keep in mind that it's not immune to discontinuity effects. So if you have something like a bend in the coax, an incident wave will still suffer reflection coefficient. Now, that can't be predicted by transmission line theory. I mean, transmission line theory would say, well, wait a minute, this is the same coax as here. I've just bent it, right? It's the same structure, so it's going to have the same Z0. You know, if one line meets the second line and they have the same zero, there shouldn't be any reflections, right? Well, in the real world, there's going to be some reflections, right? Because again, discontinuity is not something that transmission line theory accounts for, right? No radiation can escape from this band, but there'll be reflection coefficient. but we can't, it's not easy to predict. Can't use transmission line theory to predict it. You can use some kind of a, what's called a full wave EM solver, or something like HFSS or Microwave Studio, something like that, to predict it, but not to simple transmission line theory. Okay, now what about the twin lead? So here it is, the twin lead here. Here's like a cartoon little picture of like the electric field vector. The currents and the charges are equal and opposite. So if you visualize electric flux lines coming out of, let's say, the positive wire and go to the negative wire, the flux lines kind of look like that. They decay pretty rapidly as you go away, and because one's plus and one's minus, equal and opposite. And it doesn't take too far away before you get too far away before the field is pretty small. But that depends on the spacing between them, right? It's kind of almost like a dipole effect. The closer you make these two wires together, the more rapidly the field is going to decay. But from a theoretical point of view, it goes out to infinity. The field extends out to infinity. Even though it's getting weaker and weaker, it really goes out to infinity. Now that means this structure is susceptible to picking up EMI or causing EMI, right? So it can generate a field that interacts with a component over here, or a component over here that's radiating a field can be picked up by the twin lead, right? To make it more immune to that, you can space them closer and closer together, okay? Now, having said that, keep in mind that fields that go out to infinity is not the same thing by itself as saying that the line is radiating, okay? Again, it's discontinuities that cause these effects. So imagine a pure straight twin lead, nothing else on it. It's a pure twin lead that goes on forever. Is it going to have any kind of radiation? No. I'm not proving it, but here's a little picture that goes along with it. Just imagine you make like a little cylindrical surface, it goes around the twin lead like this. Maybe it's 1 meter long in the z direction, something like that. Now, although it might be kind of difficult, in theory, you could calculate the Poynting vector and take the real part to get the watts per square meter. And the unit normal to this cylindrical surface on the side here would be unit vector rho. Here's the usual ds and cylindrical coordinates. Just pretend we were able to go with a computer or something and carry out this integral over this surface here that's 1 meter long in z. What does this mean physically, this integral? That's, watts per square meter integrated over the surface S. That's the power in watts that's escaping through this surface, right? Okay. Now, you have to take my word for it, because I'm not really doing the calculation, but that integral is going to end up being 0. Okay. So if it's a perfect straight run of twin lead, no radiation is escaping. It's not the same thing that is saying there's no fields here. Yeah, there's fields and they get weak, but they go out to infinity, technically speaking. But nevertheless, they're not radiating fields. There's not going to be any radiation. Okay. But as soon as you put a discontinuity in the system, then you can not only get a reflected wave, but you can also get power loss, right? So, but no reflected wave just on the line by itself. Okay, another way of saying it is just a wave traveling down the transmission line is an exact solution to Maxwell's equations, right? And if it's a lossless line, it's not going to attenuate, no radiation escaping, right? But as soon as it hits a bend or something like that, then that can cause reflections and radiation, excuse me. Okay, here's a twin lead that has a bend in it. Now, just like the coax, a bend in it can cause a reflected wave. Even worse than coax, this bend can now cause radiation, right? It's a discontinuity, and now there's nothing to prevent radiation from actually escaping. In other words, this bend here acts like a little antenna. You don't want that, but that's what can happen. Now, radiation effects, as a general rule, as it says here, tend to get more and more serious as the frequency increases. Okay, so at low frequencies, people don't worry about it too much, but at high frequencies, it can become significant. Could be even very problematic on something like a circuit board. So if you have some kind of microwave circuit board, even a computer board operating at microwave frequencies, engineers have to worry about that, because any kind of bend in the lines on the circuit board or something could be radiating. Could be, right? Here's a twin lead this goes back to that EMI. Remember, stands for electromagnetic interference. So here's a twin lead running next to something. This could be a water pipe in a building or something like that, right? So the fields, they go out to infinity, even though they decay pretty quickly. So they're going to hit this pipe. And when the fields hit this pipe, they're going to interact with the pipe, set up currents on the pipe, and the pipe's going to be like a little antenna radiating. Now, there'll be a reflected wave due to that interaction with the pipe, and there'll be radiation from the pipe. again, radiation effects tend to get more serious, usually at high frequency. Now, again, one thing you can do to minimize the effects is try to keep the spacing between the wires as close as possible. Here's another interesting example of radiation. This is something a little bit different. Look what I've done here. One twin lead meets another twin lead. We had this formula earlier in the semester for the characteristic impedance of twin lead. I just want to point out one thing about the formula. The important thing about it is D over A, that ratio. D is the spacing between the wires, A is the radius of the wires. Now, what if I have a fatter twin lead and a skinnier twin lead, but I keep the ratios the same? If we're line 2 or line 1, D over A is the same. That means we have the same characteristic impedance, right? So transmission line theory would say, hey, if they got the same Z0, Z01 is equal to Z02, there shouldn't be any reflection, right? But not in the real world. In the real world, this is a discontinuity, right? And so not only will be some reflected wave, yeah, there'll be some radiation too, right at that junction. It's unavoidable. Again, usually getting worse at high frequency. Okay. All right. Now, so again, to reduce these effects in twin lead, make the spacing as close together as possible. The best you can do is they're touching, right? They've got a layer of insulation around them, but just bring them so that the insulation's touching. And then even better, if you remember, we talked about this before, twist them. Why does that work? Because then the two currents, they're already equal and opposite like this. But then not only that, but as you go from one section to the next, these two things reverse, right? And so you got a section where radiating currents are different here than here. So in other words, you got two currents that are kind of almost canceling because the currents are equal wires. But then you go from one twist to the next. Now the currents look like this, right? So they also change going from here to the next twist, right? So not only do you get this canceling effect between the two wires, which is good, but you get this canceling effect from one twist to the next. And that's the best you can do if you want to minimize radiation and EMI on a twin lead. And that becomes a practical Cat5 cable, right? That's why they do it that way. So here's the Cat5 with several different, twisted pairs inside of it. Okay. Now, I'll end by giving you one last effect that you should be aware of. And you might probably say more about this like in the microwave engineering course, but it's good to at least know what the term means, surface wave. Look at this picture here. Now, this could be a practical matching problem. In fact, it will be one similar to, I think, one of the homework problems you see on homework 6. But anyway, it's a matching problem. And so remember last time we talked about one of the ways to do matching is the extension line. Remember that? Okay, so you have a complex load. You could add what's called the extension line to it, a certain distance D, to convert it into a real load. And then a quarter wave transformer can change that real load to the Z0 of the main feed line. Now, this is exactly what that method would look like if you were a circuit board designer and implementing it on a circuit board with microstrip line, right? So here's your device, some component on the circuit board, and then here's your main feed line. Again, your main microstrip feed line might be 50 ohms. And your device might have some complex impedance like 100 plus J100, and you want to match the incoming main line to the device. So again, in this method here, you put the extension line and then the quarter wave transformer. Okay. Now, quarter wave would mean quarter of an effective wavelength. The effective wavelength. Remember we talked about this before on microstrip line. There's something called epsilon effective. Do you remember that? Because some of the field lines are in air, some are in the substrate, so you use something called epsilon effective. Okay, but anyway, so quarter wavelength using epsilon effective. But anyway, I just want to point out that things like this, where one line, the fatter transformer line meets this line, that's a discontinuity, right? Same thing over here, and so they'll be, even though you might design it from transmission line theory, so it's a perfectly matched system. If you analyze this with a full wave software like HFSS or something, you're probably going to see a little bit of reflected wave, not because you did the design wrong, but because transmission line theory ignores the discontinuity effects, right? So a real designer might have to tweak the design a little bit using something like HFSS to really totally eliminate that reflection. Okay, but it depends how bad it is. And of course, there'll be a little radiation that could escape, right? Now here's something that only happens like on a circuit board. It doesn't happen on something like a Cat5 cable or coax, but it happens on microstrip. Because the microstrip, remember, this is a top view, but microstrip is a grounded substrate, right? Grounded substrate. And a grounded substrate supports something called a surface wave. Again, more about that in the microwave engineering course. But it's a wave that propagates along, mainly staying close to the surface. Most of the energy is inside the substrate. It decays as you go out in the air region. But it's like a wave that hugs the surface more or less of the substrate. Think of it as similar to a water wave, right? So we have the usual wave, like a sound wave that goes through three-dimensional space, right? But if I drop like a pebble into a lake, that's a two-dimensional wave going on the surface, right? Okay, that's a form of a surface wave in water. But this is an electromagnetic surface wave that can exist at microwave frequencies on a grounded substrate, like a circuit board. So in any discontinuity, we'll excite it a little bit. And so you'll have surface waves possibly potentially running around, being excited like here. And once they're excited, they can bounce off the edges and hit other circuit components and so on. So just be mindful of that effect, right? When you hear the word surface wave, that's what people are talking about, right? It's a very undesirable thing. Worse at high frequencies, just like radiation into space is. But once the substrate gets fairly thick compared to a wavelength, I would say if the substrate thickness is more than about maybe a tenth of a wavelength or something like that, that's when you probably start to really expect trouble from surface waves. Okay, so circuit designers don't like to be in that regime where the board thickness is a quarter wavelength or something like that, because then you're asking for trouble from surface waves. Yeah, please go ahead.
When transformer for like power devices, what's the effective frequency that they can modulate? So like from 50 to 60 hertz, does it change? And we can see which cause reflective wave to be bigger than it can handle.
Well, a transformer doesn't change. Well, as long as the transformer is linear, it shouldn't be changing frequency.
Because you said C0 is in a lossy line, C0 is a function of the frequency and the material inside the cable, right?
Well, okay. Let me see if this is what you're talking about. For a lossless transmission line, of course, C0 is just the square root of L over C. So it's a perfectly fixed number. It's a real number, and it's perfectly fixed, doesn't change with frequency. Now, for a lossy line, technically speaking, Z0 is a complex number that depends on frequency. We had that in the notes. Then Z0 is the square root of R plus J omega L over G plus J omega C. And it's slightly frequency dependent. That's what's called dispersion, by the way. Okay. In most cases, I think I mentioned this though, in most cases, people don't worry about that. Even in a practical coaxial cable or something, people are going to say it's a 50 ohm cable. It's a 75 ohm cable. Yeah, we understand that because it's a little bit lossy, the real Z0 might be 50.01 plus J 0.001. We're not going to worry about that. We're not going to worry about that. Okay. Now remember, what we do worry about for a lossy transmission line is the attenuation in dB per meter. That's what we care about. Okay. We don't care about the fact that the Z0 is changed by 0.01% or something like that. We don't care about that. Does that make sense? Okay. Right. So, and by the way, since you mentioned the transformer idea, let me just make one other comment here. So notice that we're using transformers to do impedance matching, right? Go from, impedance here to an impedance here. I don't know if you've seen this in your circuits course, but any transformer can be used for that. So, normally, in the power world, power engineers use transformers to change from one voltage level to another, right? Okay. You want to step up the voltage coming out of the power plant, send a really high voltage down, the high distribution lines, because high voltage means low current, and it's current that corresponds to loss, right? You want to keep the current as low as possible, and therefore the voltage as high as possible. And then, of course, you have other transformers like the substations that step it down, right, before it goes into a factory or eventually into your home, right? So that's the main use of a transformer in the power world. But in the electronics world, another use of transformers is to transform impedance. Right. So, the voltage, if the turns ratio of a transformer is called N, N to 1, primary to secondary, then of course you have a voltage transformation ratio that's N squared. I'm sorry, N, but the impedance transformation ratio will be like N squared. So any transformer can be used in two ways: to transform voltage or to transform impedance. Again, the power world uses them to transform voltage. Electronics world really uses both. Sometimes use it to transform, impedances. But anyway, this is what we're doing here. We're using a microstrip quarter wave transformer to transform impedances. Now, it would be transforming voltages too, by the way. So in other words, if you calculate the voltage here and the voltage here, you would find that they would be different. It is acting as a voltage transformer, but we don't care about that. You know, for impedance matching, we just focus on the impedance transforming properties of the transformer, right? In the power world, they care about the voltage transformation properties of the transformer. Okay, does that make sense? And of course, a microwave engineer would never really make a transformer by actually having an iron core with a primary and secondary winding. That's what power people and electronics people do. Remember, in the microwave engineering world, we like everything to be planar, like for example, with microstrip technology. So we can get any impedance we want, like with short stubs, we can get transformers, right? Everything can be done like with microstrip. That's the way microwave engineers like to work. Okay. All right. Any questions on that? Are we doing time? Okay, let's go to notes 15. Oops. Okay, finally we get to the point where we're completely done with transmission line theory. And now the next topic, which will be in for, I don't know, this is like, I don't know, 4 sets of notes or something like that. But anyway, so we'll be in it for a little while. Plane waves. There's a couple things we'll be talking about. Waves going into some medium like the ocean. Waves coming out of an antenna, which far enough away look like plane waves. Okay, let me elaborate on that a little bit. This is kind of like your motivation for plane waves. First thing it says is a plane wave is the simplest solution to Maxwell's equations for a wave that travels through free space. A plane wave is a wave, we'll say more about it mathematically in a second, but the word plane wave comes about from the fact that on this plane here, the fields are constant. That plane is perpendicular to the pointing vector, the direction the power is flowing in the plane wave. In this case, imagine a plane wave carrying power in the z direction. So the fields will be constant on this perpendicular plane right here. Now, so remember that, you know, the pointing vector, the complex pointing vector is a 1/2 E cross H conjugate. And remember that cross product is always perpendicular to those two vectors, right? Like if I take X hat cross Y hat, that's Z hat, just as an example, right? So if you have power flow in this plane wave, and notice you have E and H that are perpendicular to each other, that's one property we'll prove pretty soon. And a plane wave, the E and H are perpendicular, but the pointing vector coming from the cross product is going to be perpendicular to both of them. So for example, a typical scenario would be a vertical electric field. And that's the type, that's the direction of the electric field, by the way, that would be coming out of a vertical antenna like this, vertical wire antenna. If the current is flowing in the z direction, okay, I'm sorry, it's called x direction. If the current's flowing in the x direction because the antenna is vertical, then the electric field is going to be, as we say, polarized in the x direction, okay? But the H is going to be perpendicular to it, so the y direction, and then the pointing vector would be in the z direction, perpendicular to both of them. So this is like the actual picture of what the plane wave would look like coming from this vertical antenna. Now the vertical antenna, of course, is really sending out a spherical wave in spherical coordinates. You see, I've tried to draw in spheres here. Now, the power doesn't necessarily come out equally in all directions. It might come out more in one direction than another. That gets into what we call the gain of the antenna or the directivity antenna. We'll get more into that when we talk about antennas. That's the last topic of the semester. But anyway, visualize a spherical wave coming out. But as the sphere gets bigger and bigger and bigger, you know what a sphere looks like, right? It gets bigger and bigger and bigger, it looks more and more like a planar front, right? The sphere is getting so big. So far enough away, you're almost going to see what looks like a plane wave. So a plane wave is an excellent model for the actual radiation from a practical antenna if you're far enough away from the antenna. Okay, so it's very instrumental to understanding this to really understand wireless communication systems, right? Which means antennas. Now the plane wave, notice that unlike a transmission line, it doesn't require any conductors to guide it. It just exists, travels or propagates, if you will, in free space. It's perfectly happy to travel in vacuum. That's one of the beautiful things that, you know, was predicted by Maxwell's equations. That's what he predicted, that you can have a solution traveling through just vacuum. Of course, long time ago, that came as a shock to the scientists. You know, you may, if you look at the history, you may recall that they were arguing about something called the ether. Somebody hear that term? They thought there had to be some kind of a strange medium existing even in vacuum that allowed electromagnetic waves to propagate. But all that turned out to be nonsense. Electromagnetic waves can propagate to 100% pure vacuum. They're a solution to Maxwell's equations. Okay? Now, a sound wave requires air. A water wave requires water, right? An EM wave doesn't require anything. It can go through vacuum, right? Okay, anyway, I already said this. It's a good model for antenna radiation far away from the antenna. Okay, a few more things before we get serious with the math here. Here's taken from Wikipedia, the electromagnetic spectrum. Now remember, as you change frequency, if you're in air or vacuum, this is the speed of light, 3 times 10 to the 8th, approximately meters per second. And the wavelength is C over F, lambda 0, wavelength in free space. So it just shows you this little picture going from, you know, kind of low frequencies, radios up to X-rays and beyond, you know, what the wavelength could be here. Here's the frequency scale here in hertz. Here's the wavelength. And some little pretty pictures to kind of give you an idea what kind of scale we're talking about. The wavelength is on the size of humans. It's on the size of butterflies. It's on the size of buildings, atoms, et cetera, right? This is something that more the physicists worry about than the engineers. But this has to do with black body radiation. So it's a temperature at which it's going to emit mostly that frequency band of radiation. Okay, but we don't worry about that. Here's a table showing different frequencies from things in our everyday life. And again, using the simple formula here, what the corresponding wavelength is. And you can scan through it. I'll point out that microwave ovens operate in what's called the ISM band, industrial, scientific, medical band, at 2.45 gigahertz. And from this formula, the wavelength turns out to be about 12 centimeters. Now, by the way, you can always just plug into this formula. Remember that if F is in hertz, C is in meters per second, lambda 0 is in meters, right? But here's a nifty formula that a lot of times people like to memorize. I'll throw it out in case you're interested. You can say that the wavelength in centimeters is the number 30 divided by F in gigahertz. So 1 gigahertz, the wavelength is 30 centimeters, which is, somewhere near a foot, right? Okay, it's a really nifty kind of rule there if you'll memorize that. Of course, 30 is approximate. That corresponds to saying the speed of light is exactly 3 times 10 to the 8th, which it isn't, right? This number should really be 29.979, et cetera. But anyway, let's see. Here's a typical radio station. Somewhere close to 100 megahertz, Sunny 99.1, wavelength is about 3 meters, et cetera. Okay. ELF, extra low frequency. That's the name of this really low frequency band that the Navy uses to communicate with submarines. Why does the Navy use such low frequencies to communicate with submarines? Wait till we're done with this notes. We'll see that at high frequencies, you really can't travel at all in lossy ocean water. Right? You've got to use low frequencies, right, to communicate with submarines. You'd love to communicate with a submarine at microwave frequencies so you can transmit a lot of data, right? But you can't do it because high frequencies just won't penetrate through ocean water. And that gets back to this depth of penetration of skin depth we'll talk about later. Okay, but anyway, of course, 60 hertz, the wavelength is huge all the way across the country. Anyway, here's some more facts. So this goes to radio and TV bands. So if you're interested, here's the frequencies for the AM radio bands, the FM radio bands, VHF and UHF. So nowadays, of course, the transmission is digital, and digital TV broadcasts mainly in the UHF band. Some of it in what's called VHF band 3 here, but most of it is UHF. So for most digital TV, it's broadcasting somewhere around 500 megahertz to roughly up to about close to, not quite a gigahertz. Okay. All right. Now, here's a slide that's kind of interesting. A couple slides actually. So when you broadcast, a wave going through space, you're going to typically use that in a wireless communication system. So, as you know, there's two main ways of communication. One is with a wired system using some kind of a transmission line like coax or Cat5 cable, right? Okay, or it could be fiber optic, but anyway, some kind of, I'll call that too, wired system. So you actually physically run like a cable or line from point E to point B. And of course, the competitor to that is the wireless system, where you have antennas, a transmit antenna and a receive antenna, right? And the waves going through space, and two competing systems. Even for TV, cable TV, you got these competing systems, But anyway, so let's compare what happens in a wired system using transmission lines and a wireless system using antennas. Okay, so let's say I'm trying to send a signal from point A to point B, and I'll call distance the R. Okay, I could have called it Z or something, but I'm just going to call it R. Now I've got my choice. I could run a cable from A to B, like a transmission line, or I could put a transmit antenna to A and broadcast a signal that goes to B. Okay. Oh, I'm sorry. Wait a minute. I forgot to get this going. Okay, now I want to try to compare these two systems and see what's better. Okay, now with our knowledge of transmission line theory, we should be able to understand this. Okay, first of all, what's going to happen with the antenna system? Now remember, it's a spherical wave. The area of a sphere is, of course, 4 pi r squared, right? So you send out a certain power, like 1 watt from the transmitting antenna, that power spreading out over the sphere. So it's natural that the power density, the Poynting vector watts per square meter, is going to fall off like 1 over distance squared, right? Now it may fall off, it may be more concentrated in one direction than another direction. That's what's called the gain of the antenna. But still, in any direction, it's going to go like 1 over r squared or some constant over r squared. So that's what this is. Now, what about any kind of a transmission line system? Now, in the real world, of course, any transmission line has a little bit of loss. So it's got this thing called the attenuation constant, right? And we already calculated for the coax, remember that example? Now, the voltage, of course, is decaying like e to the minus alpha z. Oh, z is called r here, so e to the minus alpha r. But remember, power flowing down the line is going like magnitude of voltage squared. So it's going to go like e to the minus 2 alpha r, right? So a transmission line system, a wired system, the power is going to be decaying with distance like this. A wireless system, the power is going to be decaying like this. Okay. Now, if you have a really high quality transmission line system, the alpha can be small. So notice there's not much decay initially, right? But my claim is if you go far enough away, if R gets big enough, this is always going to get much smaller than this. Now, just to try to, you can do the calculation yourself, but just to try to convince you a little bit, look what I did here. I made a plot, okay? I just plotted these two simple functions, 1 over r squared and e to the minus 2 alpha r. Now, alpha could be almost anything because it depends on the quality of the transmission line, the loss of the transmission line. I just picked some typical number, 0.1 nepers per meter, okay? I remember multiply by 8.686 to get dB per meter, right? But anyway, so look at the shape. Look at the shape. And here's R in meters on this log scale. Okay. So notice there's a crossover point. Okay. Beyond this point, which in this simple example is something like whatever it is, 40 or 50 meters, you can see that the 1 over r squared is going to be the winner. You're going to get a stronger signal, right? It's always going to be that way. There's always going to be a crossover point because eventually this kind of function is going to get negligible compared to this function mathematically. Okay. Now, to drive home the point even better in the real world, I'm going to choose some very practical systems and compare them. Okay. So the comparison of different waveguiding systems with wireless systems. Now, in this table here that I've made, I'm keeping the frequency fixed, a typical frequency of 1 gigahertz. So keep that in mind. All these numbers will change if I change the frequency, but it's a typical frequency, 1 gigahertz. Now, this is distance from, point A to point B, my distance R. So notice as I go down the table, I'm changing by factors of 10. Very tight distance, only 1 meter apart, 10 meters, 100, blah, 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 up to 100 million kilometers, which, by the way, is something close to like the distance between Earth and Mars. Okay. All right. Now, so I'm comparing, okay, wired systems in yellow with wireless systems in blue. Okay. Now, this first column is what's called RG59 coax. You can Google it and see exactly what it is, but let's just say it's a typical coax, very typical coax, right? And this is then the dB attenuation. This is all attenuation in dB as you go down different distances. This one is a much lower loss system than a coax. It's a high quality fiber optic transmission line. Now, there's two types of fibers, one called single mode, one called multi-mode. Maybe we can talk about that later. I think we will later in the notes in the semester. Don't worry about it for now. But single mode fiber is the highest quality fiber you can get. So it's a very high quality fiber optic. Okay, look at how numbers are much, much smaller, right? Okay, now, even though the fiber has a much lower attenuation than the coax, they both have one thing in common. They're both waveguided, they're both transmission line type of systems. So they're characterized by alpha, which is nepers per meter, or if you multiply by 8.686 dB per meter, right? So notice that the total attenuation in dB, in either case, is just proportional to the distance. So for example, the coax, here's 1 meter. So I can say the coax has an attenuation of 0.4 dB per meter. The fiber has an attenuation of 0.0003 dB per meter. Now, if I go 10 times the distance, it's 10 times a dB, right? Because it's dB per meter. If I go 100 meters, 100 times the distance, it's 100 times attenuation, right? 100 times a dB. So since the dB, total dB is proportional to distance, it doesn't take very long before the dB is going to kill you, right? I mean, what's acceptable? How much loss can you tolerate in a practical system? 4 dB, almost for sure. 40 dB, maybe. You have a good quality receiver. 400 dB, probably not. Probably not. And 4,000 dB, that'd be considered outrageous, right? That's an astronomical amount of loss. So how far can you practically go with a coax? You can go 100 meters, probably not a kilometer. 100 meters might be your practical limit, okay, at 1 gigahertz. On a lower frequency, okay, maybe go further, but higher frequency gets even worse. Now, fiber, okay, you can go out to maybe 100 kilometers, okay, which is something like 60 miles. So you can go across the city probably with fiber, right? It's a very high quality system. But can you go 1,000 kilometers? Probably not. Probably most receivers can't tolerate 300 dB of loss, right? Okay, so it's still going to have a limit. Now look at these two guys over here. This is transmitting from point A to point B in a wireless system. Now, don't worry about how I got the numbers. When we talk about antennas, we'll say more about that. But this is the simplest type of wireless system where the transmit antenna and the receive antenna are both what are called dipole antennas, which are basically things that look like this, just wire antennas, the simplest type of wireless system you can have. This is one where I'm using a giant NASA 34-meter dish to communicate with a dipole antenna. So this could be NASA using its giant dish to communicate with a dipole antenna on, let's say, a CubeSat or some kind of an antenna that's on a satellite out in space. Okay. Now, so if you scan down here, of course, you got that 1 over r squared. So you're going to get more and more attenuation as you go further away, right? Okay. But the attenuation, the dB is not proportional distance anymore. Okay. Instead, what's happening is you have a fixed increment of dB every time you increase distance by 10. So going from here to here, 20 dB. Here to here, 20 dB. And here to here, 20 dB. That's different than saying the dB is proportional distance, right? So notice that although the dB attenuation is increasing, when you get to really far away, it's always going to be the winner. I mean, look, so what's the crossover point with fiber optic? Okay, right here, a fiber optic cable is still the winner. Okay, you go to 1,000 kilometers, the wireless systems become the winner, right? Okay, now for NASA communicating with the CubeSat or something, it's even better, right? The numbers are even lower, but that's because of the gain of the dish, very focused beam because of the big dish like that, right? So that shows you that for very extreme distances, wireless systems are always going to be the winner compared to transmission line systems or even fiber optic systems. Okay. Now there's other things to consider in the comparison, like for example, cost and practicality and so on. Like for example, if you're communicating with somebody in space, obviously you have no choice, right? You can't run a cable up there, right? Of course. In some cases, you have a choice. Like what if you're trying to set up some kind of a router in your home and you want to connect to your computer? You have a choice. You can have a wireless system or coax running between them, right? Okay. Now maybe the coax would have lower loss, but on the other hand, that might require drilling holes in your wall or something, right? So you still prefer a wireless system, right? So there's different practical concerns when you compare these two types of systems. But just keep in mind, from a pure loss point of view, that eventually, far enough away, the wireless system will always be the winner. So if you're going all the way across the country, people are going to use these microwave repeaters. You see them on towers, right? These big horns on towers. They're sending a microwave signal across the state or even further because it's a wireless system. They can do that. Free space doesn't have any loss. The only loss you get is that 1 over r squared, but it's a lot better than having this exponential attenuation. Okay. Okay. Yeah, please.
Meters, do they require power to further down the line to increase cost?
I believe, okay, I'm not an expert on underwater cables, but you can Google it, but I believe my answer would have to be yes. I mean, if it's a passive system that doesn't have any power, then how can it amplify the signal? It wouldn't make any sense, right? I think it has to. Yeah. And that's what they're doing on these repeaters too. You see on the towers, except it's a wireless system. So a lot of times you'll have a tower and you have two horns, one pointing this way, one pointing this way. So this one is receiving the signal from way over there, 100 miles away, and then the system is amplifying it, possibly digitally reforming the signal too, and then retransmitting it out of this horn, right? So it's a microwave repeater on the tower. I don't know exactly what the repeater might look like on an underwater cable, but my guess is that there has to be some kind of active system. My guess is. Okay. Let me make one other comment here. Notice that in the wireless system, okay, when you have pretty short distances, the wireless system is not as good as something like even the coax. See this? 10 meters away, the coax has 4 dB of attenuation. The wireless is 48. Now, it's true, there's a crossover point at 100 meters, but for very short distances, the coax is better than the wireless. Do you have any guesses why that is? So if I'm just going across a room, probably, and I just want to minimize the loss, it's probably wiser to have a coax than a wireless system. Why would that be? Why do I get like 4 here and 48 dB of loss here? What's the reason for that? Any guesses? A little louder? Well, I'm not worried. Let's not worry about interference. There's no interference signal here. Just pretend a pure transmitting signal going to a receiver. Yeah. Yeah, that's basically the idea. I mean, see, the one nice thing about a coax is, okay, let's go back to the coax here. The power loss is like E to the minus 2 alpha R. Now, there's no spreading wave in a coax. You put in 1 watt at the input, that 1 watt just gets totally launched down the coax. It's getting weaker and weaker because of this exponential decay, but you're not losing anything because of spreading, right? Now, as long as the alpha times R is small, that means that you haven't had too many dB of loss going from here to the receiver. Almost all the power went to the receiver, right? Now, not true with the wireless system. You got a transmit antenna here. You got a receive antenna across the room there. This transmitting antenna is still sending out this spherical wave, right? It's going everywhere. So only a small percentage is going to the receiver, right? So you lose a lot right up front, right? So that's why in the table, you have this like 28 dB, 48 dB, even though you haven't hardly gone that far. But then from then on, it's not that much worse because it's just 1 over R squared versus exponential decay, right? And so that's why there's always this crossover point. Does all that make sense? Okay, good. All right. So we're doing time. Okay. All right. Now, we won't get too far, but let's plunge in a little bit here. So now we'll get a little bit more mathematically serious here and start our real discussion about plane waves. All this was kind of like your motivation here, so now let's get serious. Now, here's Maxwell's equations in the phasor domain, the frequency domain. Okay, now if we're in air, then of course epsilon is usually epsilon 0 and mu is mu 0. Let's go ahead and assume that because I'm talking about right now plane waves in air. We'll get to plane waves in a material later, like the ocean or something. Right now, just air. Now, if it's just air in free space, there shouldn't be any current density because the current density, if it obeys Ohm's law, is sigma times E, but there is no sigma for vacuum or air, right? So anyway, so Maxwell's equations just simplify down to this. Now, our challenge is to see if we can solve Maxwell's equations. Okay, so Faraday's law and Ampere's law, to see if we can bring out the properties of this plane wave here. That's our goal. Okay, let's see how we might start doing that. Here they are again. Now, I'd like to be able to solve for one of the two, E or H. It's kind of like saying I'm on a transmission line and I want to solve for one of the two, voltage or current, right? That's what we did with the logger's equations. We substituted one into the other one. Let's do something similar. I want to try to solve for E, so I want to eliminate H. Now, one way we can do that is take the curl of the first one and see what happens. So I took the curl of both sides here for Faraday's law. Okay, now it still has H in it, but you can see maybe how that helped me? Because now on the right-hand side, I have curl of H, and that's what Ampere's law gives me, right? Curl of H is J omega epsilon E, so substitute in. Curl of H is J omega epsilon E. So now I have an equation that has E on left and right sides. That's, that's making progress, I think. Now we've seen this term, I think, before, but we'll officially define it here. the wave number of free space. Free space means vacuum, but technically speaking, air is, almost close enough. But the definition of K0, the zero always means free space, just like epsilon zero, mu zero, right? K0, the wave number of free space, by definition, is omega square root of mu zero epsilon zero. Now, why is that definition important? Well, just look at these constants here. Now, J times minus J is, of course, just 1, so that's going to go away. And what are you left with? Omega squared times mu zero epsilon zero, right? You see that? So that just is K0 squared. And then take it across the equal sign, so get this equation here. Now, this is a very important equation. The official name of it is vector wave equation, and it's a equation for the E vector. I hope we can solve it and for the plane wave and see what the E looks like for a plane wave. Okay, so how do we do that? Okay, now there it is one more time. Okay, now so bear with me. Now you're not really responsible for the mathematics, but for those that like it, let me bear with me. Let me show you how this works. This was a homework problem. You may remember it, something called the vector Laplacian identity. Here's a arbitrary vector function V. Here's a definition of vector Laplacian. Why do I like that identity now? Oh, it has this thing twice curl, and then curl a second time, right? Curl of V, then curl, second curl. Look what we have here. Curl of V, then second curl, twice curl. So look at that. I can use that. So twice curl, I'm going to use this identity. I just take this across the equal sign. So twice curl is gradient of divergence minus vector Laplacian. Okay, so that's what I have right here. Now, I don't know if that's making any progress. I mean, does this thing right here look any easier than this? I'm not sure. Probably not. In fact, maybe it'll worse. But notice this. I have divergence of E. D is epsilon E. So divergence of E is 1 over epsilon 0 divergence of D. But the electric Gauss law says divergence of D is charge density. But there is none. We're in vacuum. So this term goes away. And I just have this. I'll put in just one second, just a minute. It's called the vector Helmholtz equation. Okay. And now, I think, if I remember right, this may have been another homework problem. But anyway, what do we really like about this thing called vector Laplacian? What do we really like about it? Remember, this is the definition of it. Okay, but what do we really like about it? What we really like about it is if you expand it in rectangular coordinates, it looks like this. The x component is just a regular Laplacian of the x component of the vector, etc. So if I take the x component of both sides, look what happens. Now, this is just the E vector. So if I take the x component, of course, it just gives me E sub x, right? That's a no-brainer, the x component of E vector, right? But here is the vector Laplacian. So just pretend this says E everywhere, right? So the x component of vector Laplacian is what? The regular, in other words, the scalar Laplacian of Ex. Now remember, if I have my vertical antenna sending out this spherical wave that's turning into a plane wave, remember I said it's going to have E vertical, X direction, remember? So my assumption is this plane wave is carrying energy in the Z direction, but it's polarized pointing in the X direction. So that's why I took the X component. Now, well, I'll pick back up here next week, but here is the starting point now. This is the differential equation that Ex of the plane wave satisfies. Just as kind of a spoiler, let me say this. It ends up being the exact same differential equation as voltage on the transmission line. So the plane wave is going to propagate in space exactly the way a voltage wave travels on a transmission line. Okay? But anyway, we'll pick back up here next week, all right? Okay, so thank you. Is the attendance form still out there? Okay, thank you.